In this lesson, we're going to be dealing with gas mixtures and partial pressures. And John Dalton came up with John Dalton's law of partial pressure. And that is basically stating that the mixtures of the gas, the pressure, is equal to the sum of the partial pressures. So basically add them all up. And so that's called Dalton's law. And then it uses something new that we did not see. We did Dalton's law in pre-AP Chem, but we did not do mole fraction. And mole fraction is actually a fairly easy concept, but man, does it trip people up. And I don't know why it does, but it really does. So we need to spend a little time on this. Think of this as a percentage without the 100%. That's the easiest way to think of that, because it's part over whole, and it's just basically leading you to what you're going to need to multiply by to get something. So if I were to tell you to take if something was 25%, there's the bell, sorry about that. If I were to tell you that take 25% of something, what would you do? You would move the decimal and multiply by 0.25. Well, that's basically what mole fraction is doing. It's just leaving out the times the 100%, so that you know what to multiply by, okay? So, we've got this new formula, I think it's on the next page. Did it get left out? Oh, no, it didn't. There it is. So the pressure is equal to the mole fraction times P total. So that's gas A, or if you have more than one, okay? So let's do a couple of calculations in this, and so we'll see what that looks like. So first one is going to be a long problem. If you thought in the last lesson that doing 3 gas laws was fun to get the answer, well then you'll really like this, because we're going to do 4, okay? We're going to do 4 different ones. So we have a mixture of helium and oxygen, and we have helium, and it's got its parameters, and then you got oxygen, and they were pumped into a tank that has a total volume of 5 liters. And so we're going to get a new volume there at the end. So it says calculate the partial pressure of each gas and the total pressure in the tank. So the first thing we're going to do is we are going to calculate the number of moles of the helium. So we're going to do He for helium. And so we're going to use PV over RT. We're going to go grab helium out of the problem. So here's our helium parameters right there. And so we would say 1 atmosphere times 46 liters over 0.08206, and then temperature is 298 K. So we throw that in the calculator and we get 1.9 moles of helium. Then we're going to do the same thing for our moles of oxygen. And here's our parameters for oxygen. So again, 1 atmosphere, and then 12 liters. That looks like I did a negative, and I didn't mean to. It's just rested my pen when I shouldn't have. 12 liters. And then 0.0826, and same thing of 25 to 06. And so that would be 298 K. So we do that math and we get 0.49 moles. So the problem here is now we don't have the same volume for either one of those, so we have a new volume. So guess what? We're going to go back and we're going to calculate the pressure of helium at the new volume. So we're going to have pressure is equal to nRT over the new volume. So we're going to take that 1.9 moles that we calculated for, plug in the R value. Did we change temperature? No, we did not. So still 298 K divided by the new volume. So that's going to end up being 9.3 atmosphere. So now we want to do the same thing and find the new partial pressure of oxygen, or the new pressure of oxygen with the new volume. So that was 0.49 moles, 0.08, 206, 298 K, and then 5 liters. So then I get 2.4. So there is my partial pressure of oxygen, there's my partial pressure of helium, and so now my P total is those two numbers added together. 9.3 plus 2.4 gives me 11.7 atmosphere. It's a lot of work for that little problem. Okay? Again, if you didn't understand what I did, just to reiterate, I had oxygen and helium. I had to figure out the moles of them individually because they were at different parameters. And then I took those moles and I calculated their partial pressures based on the new volume, because we added, in both cases, we decreased the volume for both of them, and then I added their two pressures together because the P total is equal to the sum of the partial pressures. So the next problem tells us that the partial pressure of oxygen was observed to be 156 torr in the air, and you have a total pressure of 743. Calculate the mole fraction of the O2 present. So we had that formula that we gave you earlier, so we're going to do PO2 is going to be equal to P total times the mole fraction, which is a funny looking X, which is chi, I believe. And so to solve for that, XO2, we would just be PO2 over P total, part over whole, right? So 156 torr over 743 torr. So our mole fraction would be 0.210. Sorry about the bell. No units on a mole fraction. Okay, no units. Okay? So we'll do one more mole fraction problem and then we'll keep going. So this one gives us the mole fraction, 0.708, and then it asks us to calculate the partial pressure when the atmospheric pressure is 760. So this time we're just going to do Pn is equal to the P total times the mole fraction of nitrogen, which they gave us. So it's just literally going to be 760 torr times 0.7808. So the partial pressure of nitrogen in the air is 593 torr. So that one kind of shows you how many times is that bell going to ring? That one just kind of shows you how it's kind of like the percentage. Like if I told you that oxygen was 78% of the air, and I wanted you to figure out what the pressure of the air was when it's 78% nitrogen, and I gave you a torr or atmosphere, you would literally take 78%, move the decimal, and you would multiply by 780. And so the mole fraction kind of just is almost takes out the middle step, if you will. Okay? All right, so let's see. I think that's where I want to end, and I'll do one last lesson, and then we're going to be done. So see you on the next lesson.